The next speaker is also online. This is
Hi, everyone. As Denise said, I'm Keegan Thomson Paressant. I'm a PhD student working or being supervised by Pierre Cavella at the Paris Observatory and Antoine Méran at ESO. The topic of my research and of this presentation is using gravity to search for exoplanets around the Alpha Centauri system. So thankfully, the last couple of presentations this morning, we've done a very good job of presenting the context of using interferometry to look for planets and sort of the context there. So I'm really just going to focus on the context of my project in particular. As I'm sure many of you know, the Alpha Centauri system is composed of 3 stars, 2 sun-like stars, Alpha Centauri A and B, and Proxima Centauri, which is a M dwarf that orbits a pair at about 13,000 AU. And together they make up the closest star system to ours at a distance about 4.4 light years. To date, 3 planet candidates have been detected around Proxima Centauri, with the most recent one being discovered earlier this year. But none have been confirmed around either of the A-B primary stars. That being said, in 2021, there was a potential detection of a 3 to 11 Earth radius planet around 1.1 AU of the A component by direct imaging. We also know that stable orbits exist around both stars individually up to about 4 AU. So that means that there's a very real possibility that we might find something here if the techniques work. And so with this in mind, that we plan to use a high precision differential astrometry with gravity to try and recover a planetary signal within the system. So just to have a look at how astrometry compares to other detection techniques, in particular for Alpha Centauri A, you see here. So the astrometry precision is represented by the sort of inverse exponential graphs that descend in color from yellow in black with the precision given on the right-hand side. The pink region corresponds to radial velocity measurements corresponding to a shift, Doppler shift, of about 5 meters per second. If we are able to increase our precision with radial velocity, then this region would drop further down on the graph, allowing to probe for smaller mass planets. And also it's kind of limited in the separation. So I've just hashed out anything beyond about 3 AU in separation. The blue region corresponds to direct imaging of about a 3 sigma signal recovery method, and sort of probes a very niche region of our plot here. So to summarize this, essentially, we can see the astrometry really has quite a complementary set of confirmation biases compared to these other 2 methods, allowing us to observe planets at larger separations and smaller masses than these 2 objects. So here I'm just going to flash quickly a same plot for Alpha Centauri B, and you can see it's roughly similar with some small variations in where those regions cover. When we set out to do this project, we knew that we'd encounter quite a number of challenges due to the nature of the Alpha Centauri system. First and foremost, gravity was not designed for observing this kind of object. In particular, both stars are extremely bright. You can see the values in the K-band for gravity and in the visible spectrum, which means that we have saturation problems, particularly in the pupil tracking system of the telescope. And for astrometry, pupil tracking is absolutely critical for the functioning of the method. Next, we also have some other instrumental challenges. Both stars are very resolved, displaying second and even third lobes in the visibility function, which causes phase flips or phase inversion, and this complicates the interpretation of the data. Thankfully, both stars are very well studied. We have very accurate measurements of all sorts of parameters relating to them. For example, their limb dark and angular diameters are 8.5 and 6 milliarc seconds for the A and B components, respectively. However, to achieve the desired precision of the instrument, which is about 50 microarc seconds, this equates to about 0.5% of their total angular size. So just to give you a sense of scale, there's a very small red box that they've drawn there on the shape of the sun, and that's basically the scale that we're working with. So this is a very big problem that we'll need to resolve with modeling down the track. So the first step here, what I've been spending a lot of time working on, is this problem of saturation of the acquisition camera as part of the pupil tracking system. So this is the image that results directly from the gravity pipeline. where the pipeline attempts to recover the signal of 4 diodes multiplied by a lenslet. So you end up with 6 images that tries to recover the positions of these diodes that are on the spider arms of the telescope. As you can see here, the positions of the diodes are very difficult to recover in this sort of blurry speckled mess. And so we need to try and find a system to remove a lot of this saturation and recover these systems accurately. So to do this, we generated a pre-processing method where we use models. There's a quick description here. I don't have too much time to go into the details, to create a number of synthetic images that we then feed back through the pipeline to provide accurate positions of these diodes. So once this process is complete, we end up with some much nicer images that the pipeline can use for the position of the diodes. As you can see, they're very easily recoverable and consistently so. And the modification system is automated, so we can apply it not just to Alpha Centauri, but to any other binary or system, and it works very consistently. A small disclaimer for Alpha Centauri. We have some issues, as you can see by the one highlighted in red. There is a small shift compared to the other ones on the same row, but we still have about an 80% success rate. And any ones that don't work are just stripped from the analysis at a later step, so it's not a huge issue. So before we can apply our method on Alpha Centauri, we need to verify it and ensure that it's working as we expect and that we aren't adding any biases or errors into the data, as that would be unfortunate. So to do this, we observed another target, a very well-studied binary system, Gliese-65, which is very well behaved, very well known, and does not present any of the challenges that we see in Alpha Centauri. So we can make sure that this is the case. So here I've plotted the predicted orbit with archival data and our gravity data points in red, and ignoring perhaps the most separated points here on the residuals plot, we see that we have a maximum spread of maybe a couple of 100 microarcseconds. So we can see that this is working as we want. We've also compared it, not shown here, but with some other surveys, just to ensure that we're receiving similar results to separate independent methods, and that is definitely the case, which is a good sign. So knowing that our method is working as intended, we can apply it on Alpha Centauri. So we have the same sort of plots here, predicted orbit and the residuals in RA and DEC. We have the ALMA data points in red, which is to date the most accurate astrometry measurements for this target, and our gravity points in green. A couple of notes. I've only plotted the short baseline data. We use the auxiliary telescopes, and we have large baseline and short baseline measurements. But until we resolve these issues like saturation and phase inversion, the short baseline data sets are much easier to manipulate. And only those sort of around the epoch of the ALMA data, so we can do a direct comparison. Fortunately, the spread here, the results are only preliminary. The spread is still a bit large to what we want. We would like to improve it by, say, a factor of 10 or even 100 if we can, to get to around the same precision of ALMA, if not better. And we hope to achieve that once we've finished with the steps in our resolution. So the next steps of our project, the first step primarily is mastering the biases from instrumental sources, finalize the pre-processing of the acquisition camera images to remove the saturation problems, modeling of the stars themselves to minimize effects from the full resolution, and these phase inversions. And finally, once everything is working as we intend, we can start exploiting the large baseline data sets, which will only improve precision of our measurements. After that, a sort of second phase, we plan to continue observations of conjunction events between Alpha Centauri A, B, and background stars, where we'll be able to observe gravitational lensing. And Eleanor gave a very interesting presentation earlier today, which sort of describes a bit of the principle of what we'll be looking to see there. So on the plot here, we see the predicted position of Alpha Centauri A and B with respect to background stars in the K-band, with A represented by the yellow-orange and B in the red. We have 50 of these events expected over the next 40 years or so, with the first one occurring in 2021 with S1, and the next one occurring middle of next year. So if there is anything I want you to take away from my presentation today, the first is that the Alpha Centauri system is a very difficult target to observe with gravity, presenting a number of challenges that we need to resolve or circumvent in order to properly exploit the data. That being said, solid progress is being made, and there is a very real possibility to detect an exoplanet. The odds are very good considering the methods that we're using, if there is something in the system. Finally, we hope to be able to contribute our method, our procedures to the gravity collaboration and the pipeline procedure so that others can use our methods to either for follow-up observations of Alpha Centauri or for any other target that presents similar challenges. These methods are already taken into account. So with that in mind, I thank you for listening, and I'll gladly take any of your questions.
Any question for Keegan?
Can I ask a question?
Yeah, there is a question. Go ahead, Sylvester.
Yeah, on GJ65, when I look at the residual, I think, hey, maybe it's an exoplanet there in the residual. Did you check that?
So we've looked into the residuals in RNDEC. We haven't done any fitting of the data yet, but there's definitely something that we endeavor to do, yes, as our analysis progresses. Yes, yeah. We've been working with Guillaume Bourdarot and Frank Eisenhower at MPE, and perhaps we'll be able to do something together in that regard.
Any other questions? Would it be interesting to do the same on Proxima Centauri?
We could. I suppose it's less exciting, perhaps, since we already have these 3 planet detections, whereas I suppose it's a bit more special for Alpha Centauri. But yes, I suppose feasibly we could perform similar analysis on Proxima. Yeah.
All right. Thank you again.